Hello, this is the Physics 2 Lab 6 Magnetic Molasses GT Physics 2212 by Ryan Perella. This is the final lab of the semester. Introduction. The purpose of this lab is to collect the data from a magnet falling through a conductive tube of aluminum foil versus a magnet just free falling, modeling the magnet and tube interaction using computation and the actual results, and then comparing our computation predictions with the actual lab results, and take a deeper dive into the laws of Faraday and the effect it has on real-life examples. Some physics principles. Faraday's laws mean that a current will be induced into the loop by a moving magnetic field. This induced field interacts with the magnet falling through the tube, which creates a force. This force counters the force of gravity and therefore should slow the magnet down, and the magnetic fields interacting create an induced force within the tube itself. A preview of the results. The time spent in the tube was roughly 1.5 seconds. This is longer than the free fall time. Here you can see a graph of the results in our computation as well as an image of it as the magnet falls through. That's just a screenshot of the code running, and that is a preview of the results. Some equations used are that the electric field of a dipole is 1 over 4 pi epsilon naught times negative p over z cubed. Z is a distance. Epsilon equals negative n times d phi dt. B in respect to r, which is a changing variable, is mu over 4 pi times 3r parentheses r dot m minus m, all that divided by r cubed. Again, r is the distance. B equals n times mu dot I all over 2r, and then the force of the wire equals IL crossed with B, which are magnetic field. Data from the lab. Prediction. While the magnet falls through the tube, the magnet will fall slower than if it had been dropped in free space and had a free fall, and the reason it's slower is due to the induced current. Procedure for the lab is we'll set the height to drop the magnet, we'll drop the magnet and time it in air for free fall, and then after that drop the magnet through the tube and also time it, and then repeat this to decrease variance, so multiple trials. What we observed is that while the magnet fell through the tube, the air time was slower than the air time of a free falling magnet. Here is a video of our experiment. Our data collection is that the aluminum foil tube was 47 centimeters in length or height. A free-falling magnet took 0.94 seconds to fall that speed, and it took 1.5 seconds to fall inside the aluminum tube, which is quite slower. For our GlowScript computations, we created the equations for the induced EMF and the induced force created by the induced currents. We used the formulas to calculate our variables, and then we modeled the magnetic molasses, the force that slowed down the magnet. We're calling it molasses in this lab, and the magnets travel down the tube. We model that in our code. Here is the GlowScript code we used. On the left, you can see the actual graph of the model of how the magnet fell through the tube. You can see that lasted quite some time. And then on the right, you can see the top of my code, so feel free to pause and look through the code. Most of that was taken using the starter script, which is given to us, and then using our measured variables in order to make a equation and compute that and try and model it, and then we'll compare that code to the actual real life. Here are screenshots of the rest of the code. Feel free to pause the video and look through the code itself. Some potential errors in the measurement are due to the timing and reaction time delay of measuring the magnet falling through air and falling through the tube. Also, the tube is opaque. We cannot see when the magnet will fall out, so having the reaction time of seeing the magnet fall and hitting the ground versus stopping it is slower going through the tube than in free fall, where you can track the magnet with your eyes the entire time. There's also errors in the material strength versus the material we use in our code. Dropping the magnet from various heights. We did not push it off of something. We dropped it with our hands, so it could be a change of height slightly throughout the trials, which would mess up the average, as well as dropping the magnet with slight horizontal direction, which would cause it to hit the sides of the tube and kind of bounce around and slow down as it fell. Discussion. What if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, this would create a larger magnetic field, which would then further slow down the magnet. What if holes or slots were cut into the tube? How would this affect the ring? Well, the magnetic field would decrease, and therefore the magnet would fall faster due to the smaller magnetic field. Thank you for watching.